welcome to our first in the summer events of our summer NNA program. It really is a jam-packed event. We just kept squeezing more and more speakers in. So yeah, we've got a lot of people squeezed in for the next 2 hours. So really exciting to have everybody on there. So we've got John Eldridge talking about a U battery, Mark Davies talking from USNC, MMRs for industrial heat and hydrogen production. We've got the Energy Impact Centre, Nikki Maginn talking about Open 100, who is an international speaker coming from the US today. And Westinghouse are going to share a little more details on their lead-fast reactor and their clean energy park. That's Paolo, Ferroni and Kevin Askew. Alan Woods will be joining us a little later to give us an update on our SMR, and Rich Deakin is going to tell us about summarize really about the low-cost nuclear challenge, bring it all together at the end. So a jam-packed 2 hours. What we're hoping to do today is, if all the speakers could hand on to the next one, and I'll give you a prompt with 2 minutes to go because we want to try and keep everybody to time. I obviously realize there's a lot of detail, so some of your presentations are probably a little more about signposting than maybe if there's if you don't have the time. Additionally, if you have any questions, I'm not sure within the 20 minutes we'll have time to answer them. If we do, please post a question and we can read it out and present it, ask the presenters. If not, please email the Nuclear Alliance email, and we'd be happy to share that with the presenters and get back to our members. It's worth noting today, we're videoing everybody, and we'll be sharing on the YouTube, and we'll be sharing all the slides with our members, so all that detail will be in there. We're just going to run a quick poll. Obviously COVID, this is the summer season. We just want to know, what's your preference from our future meetings? We've been doing everything virtual now, and things are starting to open up in the UK. What do you really think we should be doing for our future? Can you click on the buttons, really? We're just looking to get some data of how we should take it forward. Should it all be online? Is everybody loving the virtual? Would we all like to meet in person and have a chat, or would we like to combine the two? If you could just click and submit now on the online poll, on the poll in front of you. Have we got enough data from that, Monica?
People are still voting, so we'll just give it another few seconds.
And just, I'd like to thank you. Some of you may not know Jenny, but Jenny's helping out today. She's joined the NNA, so Jenny Pearson. So you may be hearing a lot more of her. So I'd just like to introduce you to her. Thank Monica for all that today. Excellent. So it looks like we'll be doing a few more remote virtual sessions, but more in person as well. We'll be combining the two. We are intending to have a session in September anyway, and we'll be sharing the details a little more as they get firmed up. But just to let you know, we'll be having presentations on the, where's my agenda? On the DDP, and get into nuclear, and an update from the Nuclear Institute Northwest Branch on the 14th of June. And on the 28th of June, we'll be having the developments in the PPP at Sellafield, and an introduction to social values in the nuclear sector. So hopefully you would like those virtually, and we'll have more hybrid ones. All right, I'll hand over to John now. Thanks very much. John Eldridge, U Battery from Urenco.
Thanks, James. So Monica, if you can just get our first slide up for us, please. So if we just go straight into the next one. Yes, there's a lot of information here, and I'm working on the premise that you can read faster than I can talk. So it will be just a signposting. Just very, very quickly, for those who don't know me, I'm a mechanical engineer, 40-odd years of experience in the industry. Visiting professor at Liverpool University, and I've essentially been from one end of the process to the other, from front-end design, construction, commissioning, and I've operated large plants in both the UK and overseas. So this is just a quick canter through where we are with the U battery, the high temperature gas reactor. So if we could just go on to the, and this is basically what I'm going to cover. The U battery is a small reactor. It's physically small, and it's deliberately aimed at a specific market. It's basically where the diesels tend to be now, 10 megawatt thermal output. We're looking at for a low carbon solution that is flexible and that can be manufactured in the factory and shipped out in just 1 or 2 modules. And you can just see on the picture on the right, just an indication of the plant layout. The reactor island essentially sitting in the middle there, 1, 2, and 4. And just to the left is the power conversion system. And to the right on this one, item 6, actually shows the spent fuel store. This one's showing quite a large version. It's actually got 60 years worth of fuel there in storage. And that can vary according to the wishes of the customer. So if we go to the next slide, please. And we have 2 pillars for safety. The key for us, of course, is the TRISO fuel. It's a fully ceramic core, so it can take incredibly high temperatures. So the main safety feature of this is the fact that the particle fuels the integrity is maintained certainly up to 1600 degrees C. And in fact, there's evidence that you have to get nearer to 2000 degrees to start getting any sort of distress on those fuel elements, on those fuel pieces. As I said, the reactor output is small. We have a beauty of having a graphite core, so there's quite a thermal lag in the system. In other words, you're not bounced into making quick decisions if there are issues. And it's basically, so yeah, I was just mentioning one of the beauties of this system is that as the temperature rises, the coefficient of reactivity drops. In other words, it shuts itself down. And again, that's not theoretical, that's actually being demonstrated in other reactors of this type. We go to the next slide, please. So, Monica, have you got the next slide? Thank you. So, as I mentioned before, it's small, it's robust. It has a long pedigree. The picture on the bottom right, in fact, is of the Dragon reactor down at Wimfrith. And in fact, I'm afraid I'm old enough to have actually worked on that during my training. But essentially, it's the same basic thing, the TRISO fuel, graphite core, 750 degree outlet temperatures. That was a 20 megawatt thermal as opposed to our 10. We're looking very much about reducing risk, construction risk by offsite build. And of course, the other thing we're really pushing for is autonomous operations. Basically, this thing runs in an unmanned state. If we go to the next one. So the idea is that we can deliver this in a variety of forms. If you look to the bottom right, you'll see that we essentially will have essentially a reactor island that is standard. The only thing you might get as a change is the color. We probably will do better than any color than black. But essentially the reactor island is a standard item because we believe we will need to build several hundred of these over the years. And then on the left-hand side, that's the user options. In other words, what does he or she require, whether it's, and you see it down the list, it could just be heat for the key foundation industries, cogen perhaps, pure electricity, or there will be others. And that's just showing the variety and flexibility of the system. If we go to the next slide, please, Monica. We've had really good support from BEIS and the UK government. And we've been successful with 2 phases of the AMR program, starting off in 18. I'll just have a quick slurp. And then we've got, we're currently in the second phase, £10 million program, where we're essentially developing the concept of the project, due to be delivered June next year. We also had an opportunity, which popped up out of the quite suddenly. That was last January. That was the year January, where there was further funding from the Advanced Manufacturing and Materials program, which has enabled us to go away and build a full-scale mock-up. And that is due to be delivered in the autumn of 21. And I'll be showing you some pictures of that later on. If we go to the next one, please. But of course, we're also running in a dual track here with our colleagues in Canada, where their market is quite different, but again, it's very extensive, and we're very excited to work with the various federal and state governments, and we're working with some of the major suppliers about the potential of supplying power, carbon neutral power, certainly to remote communities and to mines and so on, those that at the moment are very dependent on diesel generation. And this is another reason why the sizing of the reactor in that sense is so key. If we go to the next one, please. So in the UK market, a little bit more specific, I've mentioned the foundation industries a few times so far. Certainly we see this as extremely important, where there is a dependency on subsidized gas for those critical industries that rely on high temperatures. Of course, it's one of the major sources of emissions. And if we're going to retain those foundation industries in the UK, it'll be essential to be able to get those into low carbon. And of course, you can see the numbers, they're quite substantial in terms of jobs and numbers of companies and so on. So yes, the usual suspect, glass, paper, steel perhaps, certainly ceramics, minerals are all in that potential list. We could go to the next slide, please. So, as I said, we are looking for multiple applications, but very much making that point that the reactor itself will be a standard item, but the use of it will be many and varied. Interestingly, you'll see the second bullet down that we are also looking at working within urban settings. These may very well be against universities or supplying hospitals or whatever. The hydrogen production, of course, that's coming up very much on the rails. That's constantly in discussion. And the other things that you can see there. So the next slide, please. So we have a very strong team on the project. This is currently on the conceptual, and you'll see that we pretty well got all the leads in their particular areas. The work packages, the way this is split, this project is split as we're going through this. Probably work pack 1 is the key one in terms of the primary systems, where we've got Jacobs leading it, and you can see the various people who are supporting that. And in fact, if you look at the various leads and subcontractors, you can see people's roles changing as they, in some cases, lead, in other cases, support. And I'm pleased to say we're fully up to speed and we're starting to get the results coming in now. So it's a very exciting time for everybody. And you can see just right at the very base there, I have also included the work on the mock-up, which has been produced for us by Cavendish, and in fact will be installed at their Weston facility in the summer. So if we could go to the next one, please. So as far as the design goes, it's keeping it simple. Above all, we want it simple and reliable. We're looking at good safety through good design. We're minimizing safety components because of that, the beauties and the benefits of that core and its small size. And I've talked about the business of module build. And of course, by doing that, we are minimizing on-site working. In fact, we're trying to keep that to an absolute minimum. So if we go to the next slide, please. Okay, Monica. So challenges, of course, there are always challenges. This is just showing 2 of our modules strapped side by side. That actually forms the reactor cavity. A major part of the reactor, in fact, it's probably 40% of the footprint. Of course, by going for module build, it means we've got to get it right. We can't go picking at it like we've traditionally done in nuclear. You know, once you've got the design in, that's it, it's fixed. So In fact, it's key that we focus on the manufacturing readiness levels as opposed to TRLs. And in fact, you reverse an awful lot of things that are traditionally done. For instance, transport leads, civil leads, and the process systems have to come in and frankly work around and within their constrictions and their envelopes. So if we go to the next slide, please. I mentioned earlier that we are looking for the full-scale mock-up. So this is obviously just some pictures of it. It's principally showing the reactor pressure vessel and the intermediate heat exchanger modules. It's actually currently being manufactured as we speak in Manchester, at Manchester Precision. We've got 3D model being built alongside it, a virtual model. And that is being fed into the major advanced module work, the major conceptual work. So we're getting the benefit of being able to work the ideas backwards and forwards on there. As I mentioned earlier, it is due to be delivered to the Cavendish facility at Whetstone in August. And the idea is that in September, we have a showpiece event where the major investors, where Bays and the others come along and see what is essentially one of the first tangible pieces of evidence for this fourth generation of reactors. So, and of course, that's just ahead of the COP26. So we see that is actually quite an important thing. I'm feeling quite proud, actually. I'm running on time here. So if we just go to the final slide that I want to share with you, because we are actually building things. So these pictures, these photographs were taken just a week or two ago. And you'll see they are the mock-ups. So I do have to emphasize that of the reactor pressure vessel. And again, just to give you a feel for scale there, it's 2.6 diameter and about 10.5 meters tall. And the intermediate heat exchanger there at just over 1 meter diameter. And these are sitting down there in the workshops at Manchester Precision. And you can see that hairpin looking device, that's the cross vessel duct that is located between the two. There's always an issue about what you get out of these sorts of things, because as I say, they are mock-ups. We have taken deliberate decisions about things like putting full-scale seismic supports in there, and the idea of the hairpin arrangement means that we can install these two modules and then couple them without having to subsequently move either of the vessels to make the connections. So I'm going to hold at that, I think. So perhaps if there's any questions or any burning questions anybody wants to ask me, otherwise I'm happy to hand back to Monica.
Hi, John. We've just had one question. Two now have come in. Very interesting from Richard Ross. What nuclear characterization would these units be?
So they're C's because we depending which unit you're talking about. You're talking about the whole plant. Are you talking about the mock-up or the reactor island?
Whole plant, Richard Ross has put in the text.
Okay, let me dodge around that one because we've got as I said, the whole emphasis on this is about trying to keep minimizing the footprint and in fact minimizing the emergency zone around the plant. And in fact, we're trying to keep to the point where that actually is described by the building itself.
Okay, thank you. Do you envisage certain specific constraints for deployment from Sue Hewish?
From Sue, right? Sorry, I'm not sure yet, Sue. We're not aware of. As always, we can't just assume that you can just walk along and put one of these down because we do envisage these being deployed potentially across large industrial sites. And obviously, we've got the situation there where it's not necessarily the reactor that is the concern about, from an emergency point of view. It could very well be the plant itself. In other words, if you were putting this alongside a major petrochemical complex or systems like that, what impact would that potentially have on the reactor, on the U battery and its location?
Well, thank you. We haven't had any other questions, so that was, I just didn't realise that the plans are developed so quickly. So that was really interesting, John, to understand the developments that have been going on. So thank you for that update.
Let me just come in on that, James. Just half a thing there. Remember, we've been looking at this for over 10 years. And so with the interest from the government like that, that's been a real shot in the arm for us. It's enabled us to really push on at a decent pace now. We're very grateful for that for obvious reasons.
Yeah, it's great to see the mock-up being built. We've just got one quick question. What are your challenges for remote operation, from Chris Cox from Contra?
Well, it's probably because the biggest challenge and in fact we believe it's the biggest challenge from right across the piece. It's the nuclear culture. It's because we don't normally do that. Is how acceptable will it be? So of course we've been test flying this with our colleagues at Bootle, at the ONR, and so on. That from the economics point of view, it's essential that we can operate this plant remotely, or rather monitor it remotely, and that it can work on a genuine autonomous approach. So that is obviously one of the key outputs from the conceptual work that we're doing, just the how and what we will be doing, and of course making sure we can maintain the security of that of those systems. But we're taking key lessons from the things like the offshore wind and the various offshore facilities that operate in this way.
Well, thank you for answering those questions and keeping to time. That was a fantastic presentation, and I think you've ideally queued it up really to hear a little more about USNC and Mark Davies, really, to talk a little more about MMRs for industrial heat production and for hydrogen production. So if I can hand over now, thank you very much, John. Really appreciated.
My pleasure.
Mark, is everything all right?
Sorry, I was on mute. Hi, everybody. Could you just move to the next slide, please, Monica? Thank you. My name is Mark Davies. I'm the director for the USNC UK subsidiary, and I also have a responsibility for delivering the qualification of our FCM fuel and making sure we deliver the commercial fuel for the demonstration plant that we're planning at Chalk River on time. I spent a large part of my career working for the Pebblebed Reactor project in South Africa, and also for ESCOM, trying to keep the AGR systems going in the UK. I'm going to talk this morning quickly about our micromodular reactor, where we are in Canada, and then how we plan to pivot into industrial heat and hydrogen production. Next slide, please, Micah. So who are we? Again, I won't read everything out. USNC was born out of the Deep Burn project in the US. It's completely privately funded though, and we've had about $50 million investment to date. We have focused on Canada. We're obviously in competition with U Battery. We have a very similar product, and we are looking at remote mining communities in northern Canada as our launch market. We formed a joint venture with Ontario Power Group called Global First Power that will build, own and operate the demonstration plant at Chalk River. Next slide, please. I'll cover that in the next slide. So where we are, we have a small micromodular reactor. It's 15 megawatts thermal, delivering 5 megawatts electrical. If you choose to produce power, it can also do cogen, And we have two big innovations, which I'll come on to in the next few slides. It is centered around the fuel, as with U-battery. It's an all ceramic core. It can go up to very high temperatures, and we are basing our design on the proven robust TRISO fuel that has come out of the NGMP AGR program, but we're encapsulating that in silicon carbide. It's going to be a modular design, so it's built in a factory and delivered to site, so construction time will be minimal, and the quality of the components will be tested in the factory. We believe the cost will be very small, fraction of the large gigawatt class plants, and therefore the risk associated is also small. Next slide, please. So FCM fuel, what is it? Well, it's the standard TRISO robust coated particle fuel, and we encase that in a silicon carbide matrix rather than a graphite matrix. And that gives us a second barrier to fission product release from the TRISO. We are manufacturing this using a carbon vapor infiltration route, which gives us a very robust manufacturing route. We've started a qualification program, a complicated, time-consuming and expensive qualification program at NRG in Petten that has done previous programs for the European projects and also the Chinese reactor systems. And we hope to get fuel in core by Q1 next year. Next slide, please. The second innovation that we've introduced is we have separated the nuclear island from the adjacent plant using an intermediate molten salt loop. So that effectively decouples the reactor system from the adjacent plant. And it also protects the plant from things like water ingress, chemical attack, or fission product wash-off in. And our nuclear island is then what is licensed. The adjacent plant is separated and is not subject to a nuclear license. Our footprint, as shown on the diagram, is about 80 meters by 80 meters for the nuclear island. And we have already started to place orders for long lead items. As indicated, the key components like the helium circulator, we are working with Howden UK, and they are delivering a fully submerged circulator for us. And we are well down the track with that. We expect that work to be complete either later this year or early next year. We have got to down select a graphite supplier. As I said, we started the irradiation qualification, and we've placed a long lead item contract for the IHX, which will be a printed circuit heat exchanger type. We're already working with Aalborg on the molten salt loop. And as I say, we've established a site at Chalk River to build the first plant. Next slide, please. So just a little bit of an update on where we are in Canada. We are in VDR phase 2, and we've signed the first agreements for siting our demonstration plant with CNL and ACL to site a plant at Chalk River. We have a chosen site now at Chalk River, and we're hoping that we'll bring the first SMR into operation by 2025 is our timescale. The timescale shown on the slide is 2026 or earlier. As I mentioned earlier, we've got a partnership with OPG that will own operate that plant. We have an active application. The environmental assessment has already started, and a license to prepare site has started as well. You probably saw that in the press recently. Next slide, please. So if we want to bring this to the UK or other well-established countries rather than remote mining communities and things like that, we recognize we will have to change what we do and maybe partner with other systems and go for a hybrid approach. We already examined our design for the 15 megawatt thermal, and we can go up to 30 megawatts thermal without changing the design. What it would mean is, I forgot to mention this earlier, that we don't refuel for 20 years for the remote mining communities, which gives them a stable supply. If we were to go up to 30 megawatts thermal, we would have to refuel after 10 years. But we would do that in established countries like the UK or Europe. And that would enable on the same carcass for us to deliver 30 megawatts thermal, not 50 megawatts thermal. And we could couple that with wind or solar to provide electricity. We could provide the heat. And we're looking at various hydrogen production technologies. We're looking at thermochemical water splitting, HQ-Tech process, or we're looking at solid oxide electrolyzer cell technologies, or indeed high temperature steam electrolysis, where we may supplement the heat from the MMR with an electric heater to get it up to the right sort of temperature level. So we're looking at a range of hybrid options as a solution. Next slide, please. So where are we? As I said, we're into the environmental assessment for our plant at Chalk River, and we've started the long lead item procurement. We're working with a number of companies in the UK to do that. We've established discussions with the Indigenous public and other stakeholders in Canada in order to facilitate our plant at Chalk River, and we intend to start site preparation mid-2023 and hopefully commission and commence operation in 2025, 2026 timescale. That has been hit by COVID. So what hopefully we'll still make 2025, but it may slip into 2026. Next slide, please. So our business case for those remote Canadian sites, we think because of climate change and reducing carbon emissions, it makes sense to site an MMR in these remote mining communities. We don't think renewables present a credible alternative to replace the diesel fuel that's currently used. The MMR is an off-grid application which suits the mining application in northern Canada, and it's also a near-term solution, mid-2020s, to support Canada's carbon reduction objectives. And it's a reliable source of energy. It's 20 years of energy compared to diesel. So in all, MMR will eliminate millions of tons of CO2 emissions. Next slide. So you may have seen in the news, we are making good progress. We've partnered with a number of key suppliers and end users. So we've teamed with Hyundai as part of our EPC consortia to deliver the MMR. I've already mentioned the OPG collaboration, but we've also now signed a partnership with Synthos Green Energy to develop micromodulars to decarbonize their chemical facilities in Poland, and we have jointly bid with them into several projects across Europe and elsewhere. Next slide. So thank you very much, and with that I'll answer questions.
Has anybody got any questions? Please post them in the chat function. We've got about 8 minutes, so yeah, plenty of time. One from Lauren Jones. Quick question. You said that MMR can be used for cogeneration for maximum flexibility. What's the typical time needed to move from power to heat?
So that's a good question. Because we have an intermediate salt loop, then effectively if we're using steam production for process heat, then we can just divert that steam production across to a steam turbine set that's on standby. So it's effectively as fast as we can spin up the steam turbine, which is on standby.
Another one, I can't read. Grangecht Grange TC. For both designs, what are the concepts for transporting fresh and irradiated fuel? I guess that's a message maybe to Westinghouse, but if you could answer it, please.
What is the method? So we'll be transporting fuel element assemblies in transport casks, probably modified 55-gallon drums with extra protection, but each individual fuel element assembly, I probably didn't go into it enough, but we make pellets that are about 21 millimeters in diameter by about 30 millimeters high, and we have about I think it's just over 1,000 of those in each graphite fuel element assembly, which is a hexagonal block, and each hexagonal block will be loaded into its own individual transport canister and supplied to site. So that's fresh fuel, and then the core will be assembled on site. We have an alternative strategy where we make the core up in the core barrel and we transport the core barrel to site. And we're looking at the licensing aspects of transporting a whole core like that. That would obviously be slightly more efficient, but it may not be as acceptable as transporting the individual fuel elements. In terms of spent fuel transport, once the fuel is irradiated, we intend to remove the whole core. That could be conceivably by a cartridge replacement, which is pulling out the whole core barrel and inserting a core barrel into the core, or by individual fuel element assemblies using robotic removal and trucks. That will go into an interim store for a few years, and then they will be transported away using Holtec spent fuel canisters.
Oh, Tony Grange asked that question. So, has anyone else got any other questions? We have got a bit of time. I could probably post that question back again to John Eldridge if he's got a couple of minutes, unless anything else comes in. John, do you want to have a chance at answering that question?
Yes, I mean the way of importing the fuel, as Mark has discussed, actually is pretty well as ours, because our tools, although of course they're graphite blocks, they're graphite, but they're fuel elements that have hexagonal, and we were envisaging their import as single units. You may be aware that UKRI, that name actually came about because the idea was, in fact, to do as Mark was suggesting at one point. Could you in fact install the entire core in one? Could you then subsequently take it away as one? I mean, our timing is typical 5 years, and the idea was, could you in fact just put it in like replacing a battery? Now we've moved away from that just for now, because again we were realizing we were trying to keep this thing simple, so we were trying to stay within the sort of normal operations, refueling and so on that we're all familiar with. So we were envisaging removing that spent fuel, again, as Mark suggested then, as by using robotic systems. And then shipping them away. Again, we've been talking with Holtec as well. As I say, as you'd expect, there's a lot of work going on in parallel here. We have probably the only thing we're sort of still waiting really to see where the customer wants us to go. You recall on one of those early pictures, I was actually showing a fuel store actually alongside the reactor. we are envisaging it's possible that that's what you do, to keep all the fuel in place on the core, and then remove what could be 60 years worth, say, and we could envisage a U battery going that long, 60 years worth of fuel as you decommission. The alternatives, of course, is you take the fuel away as soon as you can. And again, that's we're following the same track as Mark.
All right, thanks, John. We've had another question in from Miguel Souza. You mentioned applying the technology. This is for Mark Davies. You mentioned applying the technology in developing countries. How would the approach be, given many of the countries still need to pass through the IAEA initial process?
Sorry, can you elaborate on the question a little bit, please?
You mentioned applying the technology in developing countries. How would your approach be, given that many of the countries still need to pass through the IAEA initial process? So I guess it's about putting reactors in developing countries that don't have the infrastructure regulation capability.
Right. We'd have to tackle that with the IAEA. It's slightly out of my field of expertise, but we are looking at countries like Indonesia, who I know have been involved with the IAEA. We're also looking at countries like Namibia as well. And so it's, apologies, but it's not really my area of expertise. So I'll have to dodge that and come back and provide an answer to that.
All right, thank you, Mark. That's really appreciate your presentation again. Oh, so Lauren's just sneaked one in. Just one more. Just looking at your closing slide, which is great, by the way. What's the developments for the USNC space?
The USNC space. What do you?
Yeah.
What? Sorry, what do you mean?
Lauren,
you've got a space on your last slide. I like the way you've branded it. It's just the elements of space travel. What's happening in that territory for you guys?
Sorry,
poor typing.
you threw me there, Lauren. Yes, we're also looking at advanced fuels for nuclear thermal propulsion. So USNC has USNC is a holding company. Underneath that, we have USNC Power, which is developing the MMR technology. But there's also another company, which is USNC Tech. And in USNC Tech, we're working with NASA to develop nuclear thermal propulsion systems using advanced ceramic fuels. So the requirements for those fuels is different to the requirements for MMR.
Really interesting. Thank you, Mark. Thanks for your presentation. Thanks for attending today. Yeah, some great questions. As I say, if we're jam-packed. Are there any opportunities for graduates to get involved in the SMR industry? I think that's a question for all the speakers. If you could answer it in just in a quick sentence, that'd be appreciated. But maybe all other speakers can tackle that as well, really. Mark, if you've got a second, for graduates to get involved in the SMR industry.
Can I come in on that, James?
Okay, John. Yeah,
we are doing. It's happening. We're doing this through the nuclear graduates training. So in fact, we've got possibly three people starting in August as part of their postgraduate training. And of course, we've got quite a lot, we've got very strong links with universities ourselves, so we're putting work in and around the universities directly. But it's absolutely key that we bring on the next generation into this, what is a very exciting time.
So I'd like to concur with John. We're doing exactly the same thing. We're running, internships for undergrads with, part-time, developing part-time qualifications. We're supporting postgrad qualification, PhDs and postgrads as well. We're doing a lot of work in the UK as well with Bristol University, and also now, well, it's nascent, but we're also working with Manchester University as well. Obviously in the US, we're doing a lot more with UIUC and sponsoring students out there. And in our subsidiary in South Africa, we're also doing the same.
Excellent. Thanks, John. We'll move on now to, that was an excellent presentation again. Great to find out. So what's going on with USNC. Nikki, can you tell us a little more about the Energy Impact Centre in Open 100, please?
Sure. Thanks, everybody. Hi, I'm Nikki Maginn, Director of Engineering Operations at the Energy Impact Center. I'm really excited to join you today and talk a little bit about EIC's plans to develop our first SMR project here in the UK, and how we're engaging with partners across the industry to maximize utilization of the existing supply chains and expertise. You can flip to the next slide, thank you. So EIC was founded 4 years ago with a simple yet ambitious mandate to rapidly accelerate the transition to clean, affordable energy. This is an incredible challenge, one of great urgency and scale that demands a new way of thinking about how we deploy energy generation assets, and one that wouldn't be possible without a robust commercial nuclear sector. So after many years of researching the field, trying to understand the roadblocks and challenges that have really stunted development of such a critical climate abatement technology, we ultimately found that to meet our mission would require a fundamental rethinking of the way nuclear projects are delivered. Next slide, please. So we're all here today because we agree on the importance of nuclear's energy density advantage. This is what allows nuclear to overhaul not just electricity, not just industry, but heat, transportation, and any other sector that consumes energy. And why nuclear is really the only one that fits the bill to scale to those heights. But as we've heard, the greatest problem with nuclear right now is cost, and most importantly, construction timelines. Overall, project costs are primarily driven by the speed and risk of construction, not the nuclear core technology. So the question becomes, how do you de-risk the project? So part of the answer is to use as much of the standard supply chain as possible. If you want to get a project done fast and de-risk it for all parties involved, you've got to stick to what you know, and that begins with supply chain. Furthermore, size matters when it comes to de-risking new nuclear builds. That's because smaller, bite-sized projects allow you to fit within a broader set of capital, infrastructure, and supply chain constraints. It also means focusing on the relatively boring stuff, elements of project development that go well beyond technology, things like access to capital, efficient project management, and streamlining the supply chain. So our goal is to enable a new framework for nuclear project development: smarter, faster, distributed deployment, simplified regulatory paradigms, and utilization of supply chains and technologies that we have available now. And to do this at scale, it means going back to basics. Next slide, please. So it wasn't enough for us just to stop there as a research organization. We decided to take it to the next step. In 2020, EIC put forth a plan in the Open 100 project, which is essentially a reference design for how to bring this concept to reality. Next slide, please. So Open 100 combines the best of three worlds: the nuclear steam supply system, which produces an incredible amount of energy for very low fuel cost; the construction standardization from the fossil industry, which knows how to quickly build plants and where the concept of skid-mounted equipment and modularization comes from; and the renewables industry, which has been a global leader in reducing project costs, increasing standardization, and innovating on business, financing, and deployment models that make the project more attractive to private funding. Next slide, please. And now we're bringing it to the UK with the goal to develop a smaller version of the Open 100 at sub 50 megawatts to demonstrate how we can build nuclear projects at a much faster pace and with economics that can leverage private capital funding. So key to our success will be engagement with the well-established UK nuclear supply chain. To that end, we've already begun lining up supply chain partners and identifying qualified vendors and manufacturers that meet our requirements and share in our vision. Next slide, please. So last month, we held a virtual supply chain event, which was attended by over 100 companies from across the UK nuclear supply chain. We were honored to have Dr. Tim Stone keynote the event and have support from the NIA and AMRC to reach such a wide audience. For those of you who may not have been able to attend, in my presentation today, I'll go over many of the same high-level points my colleagues made on EIC's component procurement and service provider needs. It's our intention over the coming months to get to know as much of the nuclear supply chain as possible as we ramp up our procurement activities. So if you're interested in learning more about our UK SMR development program, or better yet, want to partner with us, I encourage you to follow up with me after the event. Next slide, please. So I'd like to start just with a little overview of our technology. You can flip ahead for me. Open 100 is a pressurized water reactor that can be scaled from 20 to 100 megawatts. Its design focuses on the key cost drivers: construction, supply chain, operation, and maintenance. Its small size allows us to minimize risk by utilizing the available supply chain and limit custom fabrication or specialized equipment. We use a one-loop system with standard off-the-shelf fuel at sub 5% enriched uranium. The plant is designed to be site agnostic. Thinking of our longer-term vision to deploy nuclear in a way that can offset the global energy supply, we made the choice to utilize an air-cooled heat exchanger rather than requiring water cooling. We introduced modern updates such as advanced digital controls and other technologies widely deployed in other industries, but we leave the core technology the same. So the design is really well suited for the UK's performance-based and risk-informed licensing approach. Next slide, please. So in terms of engineering support, we're looking to leverage supply chain expertise across a number of disciplines: civil site design, logistics and shipping, different areas around structural, electrical, and mechanical, and really focus on the compliance with codes and standards of the local industry. Next slide, please. So taking a look at our mechanical requirements, we want to leverage as much as we can from proven technologies, both in nuclear and the broader energy industry. So as we've learned from the fossil industry success, construction of major components can be standardized and built in a factory off-site. Factory capable designs reduce the risk of construction, both in terms of time and delays that can happen due to unforeseen circumstances. Taking a look at most of the mechanical components, you'll see that they're all standard and found in any power plant as well as process industries. We've got the turbine generator set, typical in any plant that uses the Rankine cycle. We have heat exchangers, both shell and tube and plate and frame. We've got pumps, tanks, an air compressor set, filters, piping, and valves. And then for process instrumentation, we've got the indication and transmitters for pressure, temperature, and levels. These allow for clear indication in the field when doing observation of maintenance in and around the plant, but also having the transmitter supply data to the control room. We've also got, flow meters and vibration sensing devices for the critical components, such as turbines, reactor coolant pumps, and the feed water pumps. Thank you. So now for an overview of electrical. So in keeping with rapid deployment and factory-based approach to construction, we've really concentrated the plant's power systems into two kinds of primary integrated scopes of work. The first is the interconnecting grid switchyard system mounted on portable skids. At the 132 kV level, we'll have limited bus work that will allow us to integrate our high voltage disconnects, circuit breakers, instrumentation, and transformers onto a skid. The skid will also house our main step-up transformer. Another skid's going to house our low or medium voltage distribution. Our second main scope of work is going to be our integrated power and control houses, or E-houses. These are integrated turnkey structures often deployed in offshore oil and gas to house electrical equipment in a controlled and monitored environment. All of the above are going to require a really compact footprint from going from factory to site. So we're looking for vendors with capabilities in specialty transformer construction to support this. Our third system is a lot more traditional, diesel generator sets for emergency and standby loads. We plan to use multiple parallel sets in order to provide our critical and standby power needs. Next slide. Yeah, thank you. And finally, an overview of our manufacturing approach. EIC's approach utilizes Lean Six Sigma manufacturing and quality control methods, which focus on improving process quality and reducing cost. Our intention is to produce components in the factory wherever possible to minimize field labor quality inspections and to have plug and play modules that have already been assembled and tested. So for this, we're requiring skilled labor for factory quality inspections and manufacturing of integrated systems, as well as testing in that factory environment. Some big areas of importance include steel fabrication, wiring, PLC and controls, dimension validation, pressure vessel testing, automated testing, hardware in the loop, and really that traceability of the documentation. Next slide, please. So yeah, following up the supply chain event last month, we've been engaging with companies that are really eager to work with us during our procurement process. We're really excited to partner with members of the Northern Nuclear Alliance to support components, services, and expertise as we move forward with our plans to develop our first SMR in the UK. And in the longer term, help us achieve our mission to rapidly build out a fleet of clean, sustainable, and affordable energy to power the UK and the rest of the world. If you want to follow up with me directly, please send me an email at maginn@energyimpactcenter.org, or please take a note, the link here, which will take you to an inquiry form where you can fill out your company's areas of expertise and share appropriate information. Thanks so much. Do you guys have any questions? I can start by answering Miguel's question of the graduates. Yeah, we are also actively working with research institutions, national labs, all with undergraduates. So it's something that we are very passionate about and are actively working on.
Anybody else? There was the question earlier about the fuel transportation, both the concepts for fresh fuel and irradiated fuel, if you have time to answer that.
Yeah, so that's something that we are actively working with several fuel vendors to talk more in detail about. It's not something that we have some experts that can share more details if you want to get in touch with me directly.
Okay. If nobody else has got anything to offer, I really appreciate, Nikki, your time today and waking up so early in the morning to present to us and let us know what's going on with. All right, there's a question from Lauren here. Is the design new or based upon established PWR vendor?
Yeah, so we firmly we hold the position of being the most boring SMR out there. We are leveraging 1960s PWR standard design. If it ain't broke, don't fix it.
Okay, thank you. If nothing else has come through, I'd like.
Can I just chip in, if I may?
Go on, John.
Please. Yeah, Nikki, I'm not sure you can claim that title. I think we want to be the most boring. And don't forget, we're talking 50s technology. So I think we top you with that one. You know, I think the measure is if our audience has fallen asleep within 5 minutes of us starting to speak, we've won. We're okay.
That's fair. That's fair. I mean, we can definitely share the title. I'm okay with that.
Yeah, that'd be great. Yeah. Sorry, James.
Thanks for that input, John. Should we move on to Westinghouse on their lead fast reactor and their clean energy technology park? Paolo, are you available?
Yes. Do you hear me?
Yes. Fantastic. Thank you.
Okay. Very good. So thank you everybody. Thank you for the invitation. My name is Paolo Ferroni. I'm the technical lead of the Westinghouse lead fast reactor program, and the last part of my presentation is going to be about the Springfields Clean Energy Technology Park, and my colleague Kevin Askew is going to take care of those information. So next slide, please. So what I wanted to share with you is essentially a high-level overview of the Westinghouse LFR and why we selected the technology, and especially what we are doing currently as part of phase 2 of the Advanced Modular Reactor program. So in a few words, the LFR is Westinghouse, let's say, Generation 4 technology of choice. We selected this specific technology as a result of a cross comparison among pretty much all nuclear technologies, both Generation 3, Generation 3 Plus, and Generation 4 technologies. And we made this evaluation back in 2015. So we have been exploring and subsequently developing LFR technology in collaboration with several international partners for quite a few years. The main, let's say, the primary mission for Westinghouse in pursuing this specific technology is a combination between economic competitiveness and market versatility. So what do I mean with this combination? So first of all, like pretty much all the other nuclear developers, we are targeting achieving simultaneously front-end capital cost affordability to make sure that the plant in terms of front-end capital cost is affordable by a large number of utility, but at the same time, we want to achieve a step change in cost of electricity. Westinghouse probably more than any other vendor is very much aware about the importance of making the plant affordable, but also to making the cost of electricity cheap as well. This is why we have not selected a technology for example, in terms of power level, the power level for LFR is of approximately 460 megawatt electric. So we are not a micro reactor. We are not a large, let's say, traditional large reactor. We are a mid-size reactor. And the reason why we selected this power level is specifically because of economics considerations. At the same time, I talked about the versatility. So the markets today and tomorrow will be very different from the markets 30 or 40 years ago. We want to achieve flexible electricity, therefore load following capabilities. And we do that in a rather, let's say, innovative way. In other words, we don't use control rods. We don't want to perturb the nuclear side of the plant, but rather we utilize a thermal energy storage system associated and coupled with the secondary side in order to meet a variation in power demand from the grid without changing the power of the core. Based on experience and like many of you know, the less we perturb, the less we change things on the nuclear side of the plant, the better we are. So we want to keep the power of the reactor constant, but change the power to the grid by, let's say, playing with the secondary side. At the same time, we would like to achieve non-electricity missions, especially when it comes to process heat and hydrogen. The LFR is a high temperature reactor. As you can see from the table on the bottom right-hand corner, our development and deployment strategy when it comes to temperature is a staged approach, starting with a temperature up to 530 degrees centigrade in phase 1, which is the demonstration phase of LFR technology, and then increasing this temperature up to 650 degrees centigrade. So it is a high temperature reactor, and the way we plan to achieve these non-electricity missions, including hydrogen, is to combine the high temperature capabilities of the technology with the low cost of electricity. As you know, one of the main ways to produce hydrogen is high temperature electrolysis, but electrolysis is quite demanding when it comes to electricity. So the cheaper is your electricity, the better you are from the economic standpoint. And last but not least, fuel cycle advantages. And I will touch this point a little bit later. The Westinghouse LFR is a fast reactor, and therefore it shares all the fuel cycle and fuel cycle management advantages of other fast reactors in terms of uranium resource utilization, especially when combined with a closed fuel cycle, and the capability to efficiently utilize the plutonium stockpiles. And we know that in the UK, there is a significant amount of plutonium that is currently safeguarded at high cost, but it doesn't produce any electricity. In terms of, let's say, technical characteristics of the plant, the table shows some of them. As I said, it is a mid-size reactor. Regarding the fuel, and consistent with our strategy for materials, we envision a staged approach to fuel development, starting with a relatively high maturity fuel, oxide fuel during the demonstration phase, and then switching to more performing but less mature advanced fuel, and we are currently considering uranium nitride. I think you can go to the next slide, please. So regarding the motivations for LFR technology, I already touched some of these items. What we generally say is that we would like, with this technology, to achieve a high level of safety consistent with Generation 4 standards, simultaneously with economic competitiveness in terms of LCOE. So the technology itself, from the safety standpoint, is very much suited to achieve safety and meet safety requirements post-Fukushima, especially when it comes to lack of exothermic reactions between lead coolant and other materials, whether it is the cladding material or secondary fluid or air or water. And at the same time, as I said, economic performance. An item and a characteristic of LFR technology that I wanted to talk a little bit more in detail in this presentation is about the technology readiness, given that many stakeholders and many people think that LFR technology is not so mature. It is definitely less mature than light water reactor technology. It is less mature than sodium fast reactor technology or high temperature gas reactor technology in terms of having reactors that have operated at commercial scale, but it is not as immature as many people think. You will see over the next probably few days some important news coming from Russia, where their 300 megawatt electric LFR has recently received a construction license permit, and there will be the first concrete in a few days. But LFR technology is not just a Russian technology. Outside of Russia, especially over the past 20 years, there have been significant activities in R&D, applied R&D, and especially testing. And right now, the focus of the key stakeholders, Westinghouse as well as, and especially our partners, is on testing medium and large size components and systems. We have, as a LFR community, an experience of 20 plus years in terms of LFR technology, testing, not much Westinghouse itself. As I said, we started about 5 years ago, but especially our partners. And when possible, we leverage the similarities with the sodium fast reactor technology, especially when it comes to modeling and simulation tools. Also, as I said earlier, there are some advantages from the standpoint of fuel cycle and the sustainability of the fuel cycle itself. To tell you the truth, Westinghouse did not select LFR because it is a fast reactor. We know that the importance of let's say uranium natural resources utilization is high, but not as high to motivate and to drive the selection of a given technology relative to another. We selected LFR essentially for a combination between safety, economics, and also fuel management advantages. But as you know, there seems to be some indicators worldwide that the support to nuclear and the number of nuclear power plants worldwide may increase significantly, especially under the pressure of carbon reduction targets, including in the UK. And so we believe that societies and countries will become more and more sensitive on fuel cycle management and sustainability of the fuel cycle itself. And at that point, at that time, it will be too late to develop a fast reactor. So we wanted to be, let's say, proactive and have, let's say, in our pocket a technology that not only achieves our objective from the standpoint of safety, economics, and versatility, but that can also be utilized to support closing the fuel cycle and therefore to create a more sustainable fuel cycle. Next slide, please. Yeah, going back to the technology readiness level aspect, I wanted to include this slide, which is essentially a survey of experimental testing facility out of pile globally, international facilities supporting the demonstration of technologies for sodium fast reactors and for lead fast reactors. And you will be, or some of you may be surprised to see and to understand, to realize that overall globally, the number of testing facilities supporting LFR technology is pretty much the same as the number of testing facilities supporting sodium fast reactor technology. The only difference is, let's say, the geographical distribution. There are some countries that only have SFR facilities. Some other countries only have LFR technologies facilities, and some others have both, and some others have neither. Westinghouse, in collaboration with our partners and with funding from BASE, have a very important goal. In the phase 2 of the AMR program, we intend to design, set up, and operate state-of-the-art testing facilities in the UK at various institutions. You see here in Westinghouse at Springfields, also at Ansaldo Nuclear in Wolverhampton, at Jacobs, then University of Bangor, and NNL and University of Manchester when it comes to small size facilities for the development of new fuel. And the reason is because we would like the UK to host the very first let's say, Westinghouse LFR, and therefore to have a supply chain and a network of stakeholders that is, let's say, knowledgeable on LFR technology and capable to demonstrate key components, key systems, as well as materials. Next slide. I mentioned briefly about the current phase of the AMR program, phase 2. As I said, BASE is supporting us. We have received a significant amount of funding for the development of this technology. So it is a very important contribution to kickstart some important activities, especially when it comes to testing. The key goals for Westinghouse are essentially to de-risk the concept in order to make private and public investors more comfortable to invest in the technology itself, and at the same time create opportunities and promote involvement of the UK supply chain. Overall, phase 2 of the AMR program is a very hands-on program. We are executing the program in collaboration with our partners, and you see them listed on the right side of the slide. And the key deliverables, the key milestones, are not essentially design aspects of the LFR, which we primarily do internally in Westinghouse, but these deliverables are about testing facilities. And this is an area where students, I remember a question being asked earlier, where students could be involved. And we do have some university partners in the UK, and we are establishing some, let's say, arrangements to host these students, even to operate or to support the operation of these testing facilities. Very important for Westinghouse is the leverage of the Springfield site in the framework of the so-called Clean Energy Technology Park. We are operating this site. It is very important. It is, let's say, a logic conclusion and a logic decision to utilize and leverage the existing capabilities to support the development of the technology, but at the same time to enhance the capabilities of the site itself by, let's say, inviting and by hosting new demonstration facilities for LFR technology, but also for other Gen 4 and also light water reactor technology demonstration missions. And next slide. Yeah, this is just a list of the work packages that comprise the phase 2 of the AMR program. You see we have 12 work packages covering several areas of development. The coloring scheme should help you to understand whether these work packages are about testing materials, and we have several of them since, as you probably know, materials development and testing for the high temperature that we are targeting is probably the main challenge and the most important item within the Westinghouse program. And then other activities about testing components, fuel bundle, heat exchanger, pump, testing the passive heat removal system, and this will be done at Ansaldo Nuclear in Wolverhampton, as well as testing and understanding some unique phenomenon for LFR technologies such as lead freezing or heat exchanger rupture. Next slide. Yeah, and here I would like to, let's say, pass the baton to my colleague, Kevin Askew, to talk about the Springfields Clean Energy Technology Park.
Paolo, not wanting to just cut into Kevin's time, but there was a quick question asked by Matt Airy that you can maybe answer in a couple of sentences. Why did you select lead as the transfer medium over more efficient liquid metal options from Matt Airy?
Lead itself is efficient. It is a liquid metal, so it has enhanced heat transfer characteristic relative to other fluid. One of the main reasons we selected lead is because there are some safety benefits. For example, it does not react exothermically when in contact with air or water or a secondary fluid. Because of that, it allows to eliminate the intermediate circuit that instead characterizes other advanced reactor technologies. And as a result, there are some implications from the standpoint of capital cost. We generally tend to say that we want to exploit the inherent characteristics of liquid lead in order to achieve safety and economics at the same time. There is then another characteristic. Liquid lead has a boiling point of approximately 1700 degrees centigrade. So the margin to boiling from normal operating condition is of approximately 1000 degrees centigrade. And if you compare with sodium, this margin is much larger, so there is more thermal inertia. And generally speaking, safety analysis for LFR are very, let's say, boring, because the plant itself is I wouldn't say lethargic, but it has significant thermal inertia, so there is more time for the operator to intervene. So there are several reasons why we selected this fluid.
Thanks, Paolo. Kevin.
Sure.
Okay, thank you, Paolo. Hello, everybody. My name is Kevin Askew. I'm the Head of Growth and Diversification here at Springfields. And looking down the list of people attending today, I think there's probably a fair few of you familiar with Springfields. But Springfields has been around 75 years, was named as the nuclear fuel site production for UK on the 28th of March 1946, and has built significant volumes of nuclear fuel since that date. In 2020, back in February 2020, we launched our Clean Energy Technology Park, probably quite poorly timed because it was just before we went into lockdown. But anyway, we launched it in February 2020, and we just wanted to share a little bit of information with you today around that. So the first thing we've got is a video. So I'll ask the presenter to move on to the video, and I hope that works. This will give a far better introduction than I can. There you go. Thank you, Monica, for playing that. So the video probably explains far better than I can what the Clean Energy Technology Park is all about. But if you're familiar with Springfield, you'll recognise that overhead picture there. And broadly speaking, we've split the site into 3 areas. The first one being for nuclear materials management, the second one for fuel manufacturing, and lastly, advanced nuclear technologies. Broadly speaking, this is where most of these facilities are already placed, with the exception of advanced nuclear technologies, which is something quite new. If you could just go on a slide, please. So just to recap and remind you what our vision is here, is together for the first part, develop and demonstrate advanced nuclear technologies including SMR, Gen 4, fusion, and related industrial and medical applications. So that's falling in our advanced nuclear technologies. And as Paolo's just said, some of the modules for the Westinghouse LFR will be sited at Springfields. And we really do believe that this could be a centre of excellence for nuclear demonstration. The second area is to build a centre of excellence for nuclear materials management, delivering a one-stop shop to meet customers' needs in our nuclear materials management. And we've already made quite a good start here. We're already contracting for lots of metals decontamination, HEU and LEU downblend and U recovery. So this isn't just something for the future, this is actually reality now. And we're building upon the assets and capabilities and knowledge base that we have there already. And latterly, where most people are familiar with Springfields is in fuel manufacturing. But what we want to do is develop our advanced fuel technologies, harnessing the world-leading manufacturing facilities and operational excellence, which already exists at Springfields. So we're already widening out the different types and variants of PWR fuel that we can manufacture. And also, over the years, we've looked at the possibility of manufacturing REPU fuel at Springfields. Well, we're reviewing that again based upon latest market analysis and support from our senior leadership and some of our customers requesting that service from us. So that's a program of work that we're commencing already. But really today was about offering that invitation to people to come work with us, to come and collaborate. So if you do want to know more about the Clean Energy Technology Park, please do visit the website or just get in touch direct with us. Thank you for your time today. Any questions?
I think that there was a question about AMRs and MMRs and cost savings from Hamza that came through. I'm just trying to keep to time a bit, really. So if we have a bit of time at the end, we'll probably cover the questions. Or if you'd like to send through an email to the info@nuclear, and we'll post them through to you, Kevin and Paolo directly. But thank you for your presentations. That's really appreciated.
Thank you.
Alan, if you'd like to tell us a little more, updating us. You obviously gave a presentation when we opened up with the NNA a few years ago, so that was really interesting. It'd be great to see how things have developed since then. So, Alan, if you'd like to take over.
Sure, thanks very much. Good afternoon, everybody. I'm Alan Woods. I'm Director of Strategy and Business Development for our SMR programme. I'll talk a little bit more about where we're heading shortly. Just as some background for those of you who aren't aware and wonder why Rolls-Royce is doing this, Rolls-Royce has actually been in nuclear for the 60 years. We've been designing, manufacturing and operating, in fact, our own power plants in the defence side of the business. This programme isn't defence, but it is based on PWR technology, and I'll come as to the reasons why. Move to the next slide, please. I'd like to start just with some context, because this isn't any longer about just grid electricity. As the world's seeking to decarbonise, there aren't a huge number of solutions to decarbonise other sectors. We often get fixated by the power sector. That's only about 20% of the total energy we use. The remainder is coming from the heat and transport sectors. And as we decarbonise heat and transport, we're not blessed with that many options, particularly as you get into very heavy applications, particularly such as aerospace, which is a particular interest for Rolls-Royce. So we've got to look at how we can use our SMR for these other applications, and potentially they could end up being larger markets than conventional grid electricity. What this really means is we're no longer in a world where we need to be figuring out how we load follow with nuclear to compensate for intermittent renewables. This is actually about a world of how we integrate the product to do multiple functions, whether it be providing grid power, providing hydrogen synthetic fuel, heating, or even desalination in certain territories. But the big challenge here is the scale. And I'll just draw your attention to some of the facts and figures on the left-hand side here. People often miss the size of the scale of the challenge here. And if you look at some of the large companies who are building electrolyzers, Cummins in the US, it's forecasting a addressable market of 2,500 gigawatts of electrolyzers. That's 5,000 of our SMRs at 470 megawatts, thereabouts. Similarly, ITM in the UK has just built a 1 gigawatt per annum electrolyzer factory. So to power their product, we'd need 2 of our SMRs per annum. And if you look at some of the big industrial users now, the Eldridge data center is growing to around half a gigawatt, so equivalent to our SMR. And Bitcoin uses the same amount of power as the Netherlands. So you've got some huge, big electrical industrial users who, for economic reasons, may well wish to go off grid. It's just far more economically viable for them to be directly coupled to their electricity generation. So this is the world we're going to be moving into, and this is what we have to generate our power plant for. And this is really the opportunity for nuclear. But nuclear, of course, has a big challenge, and that challenge is cost. And therefore, that's the fundamental aspect of our program. How do we produce an economically, commercially investable power plant? So move to the next slide, please. The genesis of our program, it's all about market requirements, and those market requirements that deliver affordable, repeatable, nuclear generated electricity that can be commercially investable. So our whole design is driven by the requirements of this equation, the requirement of cost of electricity. And what we can do is control everything within inside the dotted line here. So everything within that dotted line is within our gift to control. Capital we can reduce risk through the design, and we can introduce innovations to how we build it. Everything outside of the dotted line are factors outside of our control, but they have a significant ability to impact on the commercial viability of our product. So I'll draw an example of this. The reason our plant is a PWR is for these reasons on the outside. We have to have a technology which regulators know how to regulate, that is compatible with existing infrastructure around fuel route or waste route, but equally which is familiar to our potential customers. And most of our customers operate or are familiar with light water reactor technology today. Equally, when we're looking at other applications where they may be thinking a pure operator rather than being a utility type arrangement, again, they need to be familiar with the technology. If they're not, all of these factors would mean we have challenges in terms of the timing to get it to market, if it's driven by increasing regulatory issues, or equally, if we can't seek a customer who's comfortable to buy it and operate it until they've seen one in operation for some time, we're in the realms of prototype that can put 10 plus years onto the overall schedule before we could even sell one on a commercial basis. So that's the reason primarily it's a PWR. Every other innovation on our power plant, you can trace back to this equation. If we can't, we question why we're doing it. We are not doing innovation for innovation's sake. We're not introducing technology just for the sake of technology because it looks neat. It has to provide a function, has to provide a purpose, and that has to be in terms of the economic delivery of this power plant. So next slide, please. We look at the components of cost of electricity. So this is specific to our plant, but it's a common theme across most nuclear, and that's a function of the fact that nuclear is high capital, relatively steady operational cost. But the key feature of this chart is people get fixated on capital cost, and we often get asked the question, what's your capital cost per megawatt? Actually, it's a very poor metric to measure your competitiveness in terms of electricity generation, because at LCOE, the electricity cost, is yes, a function of capital. Quite a large chunk of the LCOE is the operational cost. This is a 60-year life, so when you discount that back to today's value, it's still a significant chunk. But by far and away, the most heavy impact on LCOE is your cost of financing. And cost of financing is a function of your absolute capital, how long you're financing it for, and the risk, or more importantly, from a nuclear perspective, the perceived risk. And unfortunately, from commercial financiers, the perceived risk around nuclear is incredibly high. So we have to design the power plant to address all of these issues and demonstrate that we can deliver on a repeatable basis with certainty. So that's the basis of our design. And I'll now talk about some of the features. Can you move to the next slide, please? So Small modular reactor. Let me just talk about this phrase for a moment. Small doesn't mean small power in our terminology. Small means maximizing power for the physical size. So put it quite simply, there is no point having a 300 megawatt power plant if it's the size of Hinkley Point. That does not pass the economic straight face test. Modular, in the nuclear world, we often get fixated about the nuclear reactor and how you modularize that. It's a competition as to how big a single module we can make. From our perspective, this is at power station level, and modularization is about manufacturability and deliverability. It's about turning this into a factory fabricated product. It's about avoiding very large one-off modules that are difficult to make and require very expensive manufacturing facilities. So modularization for us is about having road transportable, repeatable modules. And then finally, the reactor. This isn't a reactor project. The reactor is only about 20 to 25% of the capital cost. If we don't look at the total power station, how we modularize that, how we improve the deliverability of that, then really we're nibbling at the edges in terms of improving the economics of nuclear. So move to the next slide, please. So when I talk about modularization, what's our power plant made up of? Well, there's three types of module facility associated with our power station. The first is nuclear islands. So this is the major vessels. They're not actually delivered like that anymore. They now come within their frames so that we can improve the speed of assembly. The second module facility is what we call balance of plant systems, or you'll sometimes hear it called the MEP modules, mechanical, electrical, plumbing modules. These are all standard ISO frame type size modules. They contain a collection of pumps, valve, pipework, heat exchangers, etc. And how they are assembled inside these modules dictates the function. But all of the components in those modules are aimed to be commercially available products where we can, so that we can tap into the commodity products that other industries use and therefore reduce the cost. We built one of those modules. You can visit the demonstrator module for that, Factory of the Future. You can see it in operation. And that's probably where the majority of the modules lie in our design, that type of a structure. The blue frame you can see actually provides the structural form of those modules. They stack together on the site and form their own structure. The final module facility is civils. So again, we want to remove pouring large amounts of concrete on site. We've moved all of that now to factory environment. Lango O'Rourke operate this factory already. You can visit Davies workshop and see them doing this type of module. This means that we can transport, we can manufacture all our civil structures in a controlled environment and transport them again on the back of a lorry to be assembled on the site. We are reducing the amount of civil construction, so we're moving to a much more steel-based approach where we can. Steel is cheaper and it's quicker to assemble it on the site. Move to the next slide, please. So a little bit about the factories as well. A lot of people say this is a factory fabricated product, and they think just simply saying you put it in a factory solves the problem. Actually, it's not about just doing stuff in a factory. It's about the design of the factories. It's about designing the product to be made in that factory and designing the factory to specifically make that product. That's how we get a production line approach. That's how we get the economics right of a factory fabricated solution and avoid turning it into what we call a jobbing shop. So we've put, Rolls-Royce has been manufacturing products for over 100 years now. The way we manufacture things today, very, very different to the way we manufactured them 50, 40, 30 years ago. The factory design is an integral part of the product design. Equally, when we're looking at factory design, we have to think about the cost of these factories. So factory cost goes up exponentially with weight and size of your largest component. So we need to keep the weight and size of the individual modules down. That reduces the cost of the factories. And since that cost has to be recovered somewhere, then it's an important aspect of the economics of the overall plant. Finally, size of the factories. there is an optimum size. So for us, it's to produce 1.8 units per annum is the optimum size we can produce from these 3 facilities. If we want to increase capacity, then we'll replicate the facilities. That's the way we do it. That's the most economic route to scale up. If you can move to the next slide, please. So how does this all come together? One of the key features of our plant is it is a small footprint. So that allows us to insulate all of those modules from the site conditions by mounting them all on what we call an aseismic bearing. That's a critical feature because it completely insulates the plant design from the ground conditions, which means we can standardize all of the modules irrespective of whether delivering to a benign site in the UK or to a site that's got relatively high seismicity such as Turkey. It means the modules are the same. So the plant design is the same. We're not having to redesign it for each jurisdiction. There are certain differences between jurisdictions. The requirement for HVAC is one of them. So we have a philosophy which is designed for, not necessarily with. And the best analogy for that is probably automotive, where if you order heated seats, the button will be there and it'll heat your seats. If you don't have heated seats, the button's still there. It just doesn't do anything. And that's the same philosophy here that we have on this plant. And that means we're not redesigning any aspect for specific sites. The modules all come to site and they're assembled on that aseismic bearing under what we call is our 4th factory. And the 4th factory, or the site factory, is critical to us achieving build certainty. So this factory goes up on day 1 and it comes down at the end of the build after 4 years. And it is reusable, but critically, it contains all of the craneage, and we have a swarm crane arrangement in that factory, which allows us to conduct multiple lists of modules concurrently. So we can, again, speed up the installation process. What it also does is protect us from the environment and protect the environment from the actual build site. But environmental protection in risk terms, and therefore financing terms, is absolutely key. You can lose in the UK up to 40% of your available working hours per year just due to the weather, whether it be wind, rain, snow, whatever it might be. We've completely removed that risk. So not only have we removed that risk, which significantly reduces the cost of financing, we've also introduced contingency because we can work 24/7 within that facility if needed to. It's not the baseline, but if we did need to, we could. And therefore, we've changed what is a significant risk in conventional terms to actually an opportunity for us to accelerate, or at least as a minimum, maintain schedule. Once the modules are all assembled, we roll back that site canopy and we leave the power plant to be handed over to our customers. So within our business as our SPV, where we're quite unique, is we will deliver all of this. Our business is to manufacture and assemble the whole power plant. We don't talk EPC anymore. We do not need an EPC contractor. We can take a simple turnkey contract and we would deliver this under what we call an EMA contract, engineering, manufacturing, assembly. This is no longer mega one-off infrastructure project. This is factory repeatable product delivery. Move to the next slide, please. So what does this leave us in terms of economics? We believe we can deliver this power plant for £35 to £50 per megawatt hour. The range is driven by that financing cost. That's where the majority of the uncertainty is. So as we build out a fleet, we would hope to come to the lower end of that, as we can demonstrate by doing that we can deliver this plant on time and to budget. And at £35 to £50 per megawatt hour, we're more than competitive with traditional fossil fuels, but importantly, we're competitive with other renewables. And if you factor in the intermittency cost of renewables, i.e. with battery storage, then actually we're far more competitive. And dispatchable clean electricity in the future is going to be a real commodity in demand, particularly as we're looking at industries who are seeking to run 24/7 operations to produce hydrogen or synthetic fuel. They'll need to do that to generate the scale. The notion that we can just use the surplus wind when the demand on the grid isn't there to generate hydrogen and solve the world's problems couldn't be further from the truth. The scale is dramatic. Dispatchable clean electricity will be needed at a significant scale. Move to the next slide, please. So just talking about some of the regional benefits, our program has been operational since 2016. We've been working with a large number of institutions that sit in all these regions already and supply chain companies. That is about to expand quite considerably. From our own business perspective, as we move into the next phase under the LCN program, which Rich will talk about in a moment, we will be growing the team to about 800 people from about the 300 it sits at the moment. So that's direct hires we'll be making. We'll equally be engaging with the supply chain, and we're working with UK government now, where we hope to have the right signals that we will start building these module facilities from around about end of next year. We will be entering generic design assessment hopefully end of this year. And if all goes well, as I say, we'll be engaging the supply chain and starting building these facilities quite soon, sooner than you would, than many people realise. And lo and behold, this is the Northern Nuclear Alliance. I'm a Northerner, and I'm really pleased to see that so much of the activity around jobs, around new facilities, around the supply chain will be happening across our region. So next slide, please. So just where we are on the programme, we had our concept phase, which ran from 2016 to 2019. That was solely run by Rolls-Royce. It was at that time where we submitted a proposal to the UK Industrial Strategy Challenge Fund, and that was accepted, and we began work under what is low-cost nuclear. That's the Industrial Strategy Challenge Fund led by UKRI. In 2019, we just completed the first phase of that, and we're now moving into the next phase, which will be a £210 million funding from UKRI, matched by 300 to 350 million from industry. And at this point, crucially, we're forming a special purpose vehicle. So this will be a separate legal entity, and there will be additional shareholders alongside Rolls-Royce who will take this program forward alongside UKRI in delivering LCN phase 2 to get us over that GDA step 2 and to the point where we then start commercialisation. Commercialisation being the point where we start manufacturing first units. So we need to have those facilities that I spoke about up and running by 2024 to start that commercialisation phase. Rich will talk more about this, I'm sure, in his presentation next. So move to the next slide, please.
Hi, sorry,
yes.
I'm just very conscious that we're trying to finish at 1 o'clock, and we have the funds a bit. So
this is my summary, so I'll leave it there and hand over to Rich, who can talk more about that phase anyway.
Thanks for your help. Really great presentation, Alan. If anyone has any questions, again, just contact us at the info@Nuclear Alliance. No problem at all. All right, thanks, Alan. Cheers.
Okay, so good afternoon, good afternoon, and thanks for the opportunity to talk about this. I think, as Alan's just made the point, this is absolutely a here and now and very live programme. UKRI, under the Industrial Strategy Challenge Fund, have been actively progressing this with Rolls-Royce and their industrial partners under the form of a joint collaboration agreement for about 18 months now. Yeah. So I normally whiz past the first slide, but I just think, just to make the real point again, nuclear power stations are being designed here to be built in factories, and factories are concurrently being designed to build nuclear power stations. So this is not about a gigawatt project. This is actually about creating an infrastructure and a program that can deliver a scalable product and ramp up rapidly to make a real impact on net zero. Next slide, please. So, continuous program initiated in November 2019 with Rolls. It's a collaboration of UK industry in response to the Clean Growth Grand Challenge to bring forward and enable small nuclear. The 3 elements to the program, and I think the key point to make here is that in total, this will be in excess of a £500 million program that will run for around another 4 years to get to the end of GDA phase 2. Come back to that. 3 work streams: innovation, This program does almost everything but focus on the reactor plant. So it very aggressively takes a holistic view to cost reduction, risk reduction, and delivery certainty. And the innovation really in this program is centered around bringing together component parts in a low-cost manner. It's not necessarily cheap, it's an efficient and effective manner. And there's just a few signals as to what that is. So UKRI working that with the industrial consortium, that was shortly switched to a special purpose vehicle, which will be led by Rolls-Royce. Rolls clearly are leading commercial market development, although we assist appropriately whenever we can on that. The third aspect of this is policy development. It will not have escaped a number of people on this call's notice that about 3 weeks ago, the UK government opened its EDA portal and invited requesting parties to apply for generic design, to enter the generic design assessment process. That is a first policy statement beyond energy white papers that sits within the business case for low-cost nuclear challenge and said, well, clearly, the only way to take this forward will be through a series of policy developments that will move in tandem and in parallel, subject to ministerial sign-off and approvals that can come together. Next slide, please. So I'm not really going to talk much around here because Alan's done that. 440 megawatt output is now 470. That's as a result of one of the innovations, which is actually removing boron from the core chemistry control system. So that's gone up a little bit. It's a 60-year life, compact design. You get the same view there in terms of the factory built, isoflake modules, standardized raft, assembled on a site under an environmental canopy, which is the fourth factory. Really important thing, I have a very northern accent. This is very key to my drivers on this program. This will be a dispersed supply chain that operates across the regions. Actually, the Northwest Nuclear, or the Northern Nuclear Alliance, sits smack at the center of that. So next slide, please. So a little bit of a slide about what's really driving this. And the answer is, what's driving it is to create a different delivery model. So this is not a gigawatt project. We are creating a product. Yeah. What's good about a product? Well, we can have much faster delivery times based on factory build cycles. We can have essentially repeated assessments where the single design, everything above ground level and the seismic bearing, is to some extent, providing we select the right envelope, ensures that we don't have to reassess each site deployment. We move from being very labor intensive on a site to high value manufacturing technology. I'm really pleased that, to say that I think this program will be a huge driver for shifting the dynamics in terms of EDI, equality, diversity and inclusivity in this sector, and making it much more attractive to work in rather than the traditional heavy industry site construction project. Tested modules, high level of product standardization. Alan's already said that's around 90%, how we put it, and the site canopy. I will linger just a second on the resultant costs. These move around a little bit, and Alan's already talked around the 30 to 50 for nth of a kind, but the key point here is very, very competitive on a like-for-like basis. I'll just stress what that means. Within the economic analysis that's underpinned the business case for this, we have added system costs into this to ensure that we are comparing LCOE against other low carbon energy sources or renewables on a like-for-like basis, and this product will be competitive. Next slide, please. Little bit about more policy enablers. This is very much seen now within the ministerial community and central government as creating a pathway to small nuclear. The £215 million that will be more than matched by Rolls was announced in the 10-point plan for green industrial revolution, and that is in essence my program that I am sharing and working in collaboration with Rolls-Royce. Yeah. It also signalled additional funding in there, which you can see, so I'll not go through that. Last slide. So it's a here and now program. So the timeline now is a little red line that sits in the middle of that. You can see some of the ambition and some of the typical things you would expect. The way I would describe this is, to be candid, if I was sitting in advanced modular reactor space and some of the other presenters on this call, I would be really quietly supportive and a cheerleader for this program, because this is the tractor that will create government policy as a trailer. So this is very much driving decision making now in central government and timing of, for example, the GDA process opening. Alan's already talked around how soon factory build programs may be initiated. That's within probably about 18 months' time. And at that point, clearly, the last point I'll make on this is nobody will do this for one. So we are building an infrastructure that's scaled approximately at 2 units per year, with an ambition to be on grid around 2030, 2031, but able to scale up rapidly beyond that. And next slide, I think, is just inviting questions, which I'll be delighted to take. I'm sure me and Alan will do a double act on this. Thank you.
Thanks, Rich. Really appreciate it. Has anybody got any questions? I think you answered Hamza's earlier question, really, about cost per unit cost. Anybody else? Wailu, what are the effluent treatment requirements for these plants, and have these been included in the considerations?
Alan, do you want to take that? I mean, have they been considering the costing considerations? Absolutely. So the costing numbers and the analysis that underpins the business case for this, to my knowledge, has had 3 independent assessments on behalf of UK government, and I'm sure there's many more being done on behalf of the consortium Rolls-Royce themselves. So in terms of the cost considerations, yes. Alan, technical?
Yeah, absolutely. They're a key part of the design, and Rich touched on one of the innovations that we've done in phase 1, which has actually resulted in the power increase to 4 and 3. That has had an impact on some simplification of some of the effluent treatment systems on the liquid side as well. And so it's a traditional PWR. So yes, we have in principle the same effluent treatment issues to deal with. We've got innovations which have helped some of them. That one on the liquid side, we've completely reduced, if not removed, gaseous discharge as well. So there's differences, but it is a conventional PWR. All the costs are in there. They're all part of the integrated design approach. And it wasn't part of the question, but I will include it just for completeness. All our costs of waste management, fuel storage, decommissioning are included in that LCOE as well.
Anybody else got anything they'd like to ask?
James, if just while people are thinking, I just make the point that I sense this is for everybody on this call with Paolo and everybody, that obviously we've been looking very much at the back end of this process, you know, including the ultimate decommissioning, and that's part of our studies through the phase 2, and obviously the just as Alan and his team have been doing, they're obviously looking very, very carefully at the individual components that ultimately could end up as a waste stream on here, and how do you get those out? How do you minimize them? So we've no excuses. We know these things have waste streams. We know there are things that have got to be removed at the end of life, and we've got to have a good, solid and costed answer to every one of those.
Alan, there's a question about rate of ROI for potential investors in the programme. Has it been considered?
Of course it has, yeah. So ROI, there's 2 aspects that are consideration on it from ROI, return on investment, for those of you wondering. The first is for those investors investing into our programme, into our SPV. So Rolls-Royce is one of them. And clearly Rolls has a capital allocation process which considers all the types of investments it has on its plate. So we have to demonstrate that this represents a solid return on investment for the Rolls-Royce shareholders. That's the first thing, and any of our other shareholders who will come in. Second is ROI from a customer perspective, where they're buying the plant, and there's different sides to the coin here. One is this pure LCOE, so the cheaper you can generate electricity at cost, then clearly you've got extra headroom there for anybody to make a margin on that when they sell electricity to whatever end application they're selling it for. The other more interesting one is the ROI to a heavy industrial user who, as they're seeking to decarbonize and they might be buying electricity from the grid today, their counterfactual being grid is far more expensive than if they were to buy electricity locally or directly from an SMR. So there, it's a cost of doing business to them, and therefore the ROI is against that counterfactual of what their alternative is. And when they're heavy industrial users, i.e. lots of electricity, going renewable, it's just not an option for them.
James, can I just make another little comment? Because I did go through it quite quickly in the interest of time, but I think the real key point here is that this is a very concurrent and rapidly accelerating program. So the design, Alan hasn't said it, but I will. The design has just passed an internal maturity review, which is quite significant, that says the design of the power station is now fit to move into the next phase and towards entry to the GDA process. And as Alan said, the Rolls anticipate applying for that and being in that GDA process this year. I think one of the key issues here is the manufacturing systems integration that Rolls brings with its partners. And that may be serendipity with COVID, but actually the level of digital engineering and integration across the supply chain that's already evident in this program is very, very high, which is very promising. There's also an issue around, obviously, licensing. Well, licensing moves forward early, so there will be no retrofit, which has often been a problem for for vendors coming into the UK. That shouldn't be the case in this program. And I think really importantly is I sit in this great spot where I actually pivot between challenging Alan and his team and the Rolls-Royce team and the partners to deliver effective solutions, but also challenging government ministers and government policy officials to deliver policy enablers at the right time. So it's a great place to be, and actually all those things are coming together. It's a very exciting time for UK nuclear in the sector.
Any other questions?
And James, if I can
Go
answer.
on.
Yeah, one of the questions about effluence, since it was, I believe, for all the panelists. In the case of LFR, we give a great emphasis and focus on the aspect of lead management. In fact, one of the topics that we selected to discuss specifically with the UK regulators and especially with the environmental agency is the topic of lead management during operating conditions, but also and especially at plant decommissioning. So from the Westinghouse LFR standpoint, plant effluents are definitely taken into consideration from early design stage.
Thank you, Paolo. It's good to hear. I've got one other question here from Prince. How does an engineering, manufacturing and assembly project model compare to using the standard using the standard EPC project model? Sorry, I've got an aeroplane flying.
So yeah, just a question. Yeah, it's quite dramatically different. So EPC is very, very high capital, very complex commercial structure. You typically have a technology vendor. You will have other parts of other suppliers providing other parts of the plant. You'll have an EPC contractor trying to pull it all together. You've got huge amounts of site activity. It is a major infrastructure project. Contrast that with ours. 90% of the power plant by cost is done in factory environments, and therefore we don't need an EPC to tell us how to run a factory. We run factories as our core business. That's what we do. As a result, this is a product, not a one-off mega infrastructure project. Equally, we can therefore take a single contract, and we'll take that single EMA contract to deliver the product out of those factories and assemble it on site. So we've done away with many of the complexities that you'd associate with the traditional infrastructure EPC project, and it just doesn't fit with us. It's just not appropriate now for the way we're delivering this. As I've had on one of my slides, the focus here is on a new way of doing nuclear, and that's EMA. You're on mute, James. James, you're still on mute.
You're still on mute.
Sorry, it was the aeroplane that did it. Do you see any risk with other countries progressing their own designs and proving commercial application before the UK does? I know the global market for SMR, AMR is so large, so hopefully not.
Yeah, I think there's a couple of things. I'll try and answer this, to be fair to Alan, because I can probably take a slightly more agnostic view. Yeah. Well, first of all, it's not a simple thing to translate a design that's being designed for, say, a North American market into a UK market. It's certainly not easy to translate regulatory acceptance, although there may be some elements of risk assessments and some of the engineering assessments that are common. Yeah, so I think it's quite easy. I think you have to be fairly forensic and look at the reality of how difficult it will be and where Rolls will be positioned in terms of being on a UK grid. So that's point number one, yeah, without speaking too specifically. I think the second point is the global market for SMRs is enormous, as is the global market for the services to manufacture components for SMRs and take them forward. So potentially the big win for this, as well as making a real impact on net zero and the target for the UK, the big win for the UK here, and this is why government's investing the money, is to create an infrastructure that can position the UK as a global leader, both with its own sovereign technology and also the capability to leverage and support manufacturing of other technologies. So we can become a manufacturing hub, we can become a leading regulator, and we have our own technology. So I think there's kind of an holistic view, James, to take, or whoever the question came from. So I hope that answers it. So the answer is no. And if myself and Alan can't get this onto grid for the opposition or the other people entering the market, I think we've failed. And actually, it doesn't really matter, because the point is proving the delivery model and get in there. And then this will be what it will be. It'll then be down to the economics.
Thank you, Richard. I think you answered that question. I think it was more of a general question anyway, so really appreciate it. I'm going to bring today to a close now. If anyone does have any questions, as I mentioned, just get in touch with our NNA email, info@Nuclear Alliance. So please drop us in there. Please drop us a note and we'll share with the speakers. So I'd just like to thank everyone. It was an excellent event. It's really exciting for the future, really, to avoid the catastrophic climate change issues we all face. So it's a really exciting time for new nuclear, and I think this is the solution, really. So hopefully it's updated our Northern Nuclear Alliance members on the developments in various areas, both nationally and internationally, and highlighted how we can all get involved. And that may not be at the tier 2, tier 3 level. We've got a number of tier 4 suppliers, so you may be a pump manufacturer or something. So it could well be exciting times for getting involved. So thank you to everyone, to John, to Mark, Nikki, Paolo, Kevin, Alan, Rich, everyone for your involvement today. It's been a real education for myself and hopefully others as well. So unless anybody else has anything they wish to share, I'll bring it to a close now. So thanks very much. And don't forget to tune into our next NNA session that we've got next week, next Monday at a similar time. It's on the DDP project, with also some updates on getting to nuclear and the Northwest branch. So next Monday, tune in. It's a shorter session anyway. So thanks very much, and feel free to log out now, and we'll see you all again.